Does your facility have jobs with tasks that involve a high degree of repetitive lifting? These could be tasks that seem relatively routine on the surface, but often leave your operators sore, fatigued, or possibly even injured. Well, it's important to note that back injuries are amongst the most common types of occupational injuries out there, and they're often preventable. My name's Matthew Romo, and I'm a human factors engineering and Lean Six Sigma professional with over 25 years worth of experience helping people such as yourself learn how to redesign jobs for operators in the field so that they are safe and effective. In this video, we're going to talk about using the NIOSH Lifting Equation to identify risky lifts and develop a lifting index to help you better understand which lifting tasks in your facility are safe and which should be redesigned or preferably eliminated from the task altogether. So let's get right into it. Now, the NIOSH Lifting Equation is probably the most frequently used tool by occupational ergonomists to determine whether or not a lift is safe or not. It was developed in 1981 and it was revised in 1991. So we will be teaching you the revised NIOSH Lifting Equation. And this equation calculates the risk of a lift and allows us to prioritize when analyzing multiple lifts which ones that we want to redesign first. And so ultimately is a risk assessment tool. And as part of this tutorial, we're going to be doing an example. I'm going to walk you completely through the NIOSH Lifting Equation and all of its components, and then we're going to do an example. There is a spreadsheet that I have developed that is downloadable. The link is in the description below, and I highly encourage you to stop the video now and download that spreadsheet, which we are giving away for free, and do the example when we get to it right along with us. Do this like a follow along exercise. So let's talk about the actual parameters that go into the NIOSH Lifting Equation. I'm going to give these at a very high level at first right now, and then we're going to do a deeper dive into each of these variables. So if it sounds like I'm going through them relatively fast, don't worry, we're going to circle back and revisit all of these again. So the various parameters that go into the NIOSH Lifting Equation are, first of all, the weight of the load being lifted. And that weight is obviously an important aspect. The heavier an object is, the harder it is to lift. And the equation starts at 51 pounds. Anything over 51 pounds is automatically considered an unsafe lift. And then all the other parameters that are measured as part of evaluating the lifting task work to modify or reduce that 51 pounds to something less, depending upon how dangerous that particular parameter is deemed to be. Now, other parameters that can modify or change our recommended weight limit start with the horizontal location. And that is the horizontal location from measured between the ankles to outward from the body to the center of the hands or the center of the load that is being lifted. And that's actually measured twice, once at the origin, H sub O, and once at the destination, H sub D. So you're actually going to be calculating the recommended weight limit twice, once for the H at the origin and once for H at the destination. And you're going to take the one that has the lowest recommended weight limit. The next parameter that can impact our recommended weight limit is the vertical location of the hands above the floor. So that's measured from the floor to where the hands are at the both the origin of the lift and the destination of the lift. So once again, just like with the horizontal location, we're measuring the vertical location twice. And those are also going to factor into the recommended weight limits at the origin and destination of the lift. Again, you're calculating recommended weight limit twice, and you're actually going to end up with two lifting indexes as well. And you're going to take the highest resulting lifting index as part of your calculation. The next one is the vertical travel distance, and that is the distance from the origin, vertically, from the origin of the lift to the destination. Now, that's not always from somewhere lower to higher. That can actually be from somewhere higher to lower. So vertical travel distance is actually more of an absolute value vertically, so either going up or down. And then there's the asymmetry angle, and that's the amount of twisting that happens with the body. So if we're lifting straight up and down without twisting, the asymmetry angle is 0. However, if we're picking up a load and then turning or twisting to, say, a conveyor belt that's to our left, that would be an asymmetry angle of, say, 90 degrees. And then there's the frequency of the lifting task as measured in lifts per minute. And that can vary anywhere from a fraction of, say that you only lift once every 5 minutes, well, that's 0.2 lifts per minute. And it goes all the way up to about 15 or so before the lift is automatically considered unsafe. Then the duration of the lifting task over the course of an 8-hour day. Is the operator lifting for the entire 8-hour shift, or are they lifting for a portion of it? Between, say, just an hour or 2 out of the 8-hour lift. If they're lifting all day, that's more dangerous. That's a more dangerous lifting task than if they're just lifting for a portion of the day. And then there's the coupling quality. How well can the operator hold the load? Are there handles, or do they have to push their hands into the side and use the friction of their hands to hold it? Is the load slippery? Is it an awkward grip? All of those things factor into the coupling quality, and that can impact our recommended weight limit and our lifting index as well. So all of these factors come in to help us calculate our recommended weight limit. And again, I'll repeat, we're calculating actually 2 recommended weight limits, one for the origin of the lift and one for the destination. And we're going to take the recommended weight limit that's smaller and then the lifting index that's higher. But we'll get to the lifting index. The recommended weight limit is our load constant, which starts at 51 pounds, multiplied by all of these multipliers. We're going to get into how to calculate all these multipliers here in just a minute, but these multipliers are all fractions from 0 to 1. Now, when you multiply any number by a fraction, it decreases. So all these multipliers actually serve to reduce the recommended weight limit, and the more risky that particular parameter might be, say the vertical multiplier, is considered to be, the smaller that fraction is going to be and the bigger bite it's going to take out of our load constant of 51 pounds. So all of these factors basically are an assessment of how dangerous a lift is on that particular factor. And then as that factor makes the lift more dangerous, that multiplier gets closer to 0 as a result. And then what do you do with that recommended weight limit once you calculate? Well, we use it to calculate what's called the lifting index. And again, just like we're calculating 2 recommended weight limits, one at the origin, one at the destination, we're going to actually calculate 2 lifting indexes, one at the origin and one at the destination. And the lifting index is simply just a ratio of the weight of the object or the load being lifted and the recommended weight limit. And this lifting index is the number that we're going to use as kind of the yardstick to determine, is this a safe lifting task, or is it an unsafe lifting task? And of course, with many things, there's a range that we are primarily concerned about. So in general, anytime you have a lifting index of less than 1, that's a good thing. That means that this is a very low risk lift and really no action is required. This is a safe lifting task if your lifting index is less than 1. But as we start to increase, the level risk begins to rise. So if your lifting index is between 1 and 1.5, that's still considered low risk. But when you get into types of tasks where it's a low frequency lift, but they're lifting a lot of weight, that can actually get dangerous. So if that's the case, then this lift should be redesigned or eliminated from the task altogether. If your lifting index is between 1.5 and 2, that's considered a moderate risk, and you should redesign that task to lower the lifting index to be less than 1. And when the lifting index is between 2 and 3, that's considered higher risk. And just like with the moderate risk, our job is to redesign that lift to be less than 1, but now the sense of urgency of the priority is higher, and subsequently, when the lifting index is greater than 3, that's considered extreme risk. And just like the other two, we want to redesign that lift to have a lifting index of less than 1, but now with a lifting index of greater than 3, that's now a very high priority. And where does this come into play? Well, if you're only analyzing one lifting job, then basically anything over 1 needs to be redesigned. But if, let's say, you're analyzing several tasks within your facility, several different, and they're all different, which one do we tackle first? Which one do we give a higher priority to? Well, the ones with the higher lifting indexes should be done first and then work down from there. So in a nutshell, the bottom line is that any job with a lifting index of greater than 1 should be redesigned to lower the lifting index. Or, you know what? Ideally, in any case, lifting should be redesigned out of the task completely. If you can eliminate the lift and automate it, or give some kind of lifting assist, that's even better, because now we no longer even have to do this calculation. The operator or the person is no longer lifting anything. A machine or some kind of lifting assisting device is doing it for them. So that's always preferable. But if you can't do that, then try to get the lifting index to less than 1.0. So let's get into how do we calculate each of these multipliers. So we are going to start with the horizontal multiplier, and we're calculating this twice. Once, and the horizontal multiplier is 10 over h, and the h is the horizontal location of the hands from the floor between the ankles to outwards from the body to the point between the hands, and that we're going to have two h's that we're going to use. So we're going to calculate the horizontal multiplier twice, once for h sub o at the origin and once for h sub d at the destination. That's going to give us two fractions between 0 and 1. The next is the vertical multiplier. And just like with the horizontal multiplier, we are going to calculate that twice. Once for the origin of the lift, v sub 0, and once for the destination, v sub d. And the v is the vertical location of the hands from the floor to the center of the load between the hands, as measured from the floor. And if you need to, use a plumb line to help you determine that straight down measurement. The next one is the distance multiplier. Now, because we're using v to calculate this, v sub d minus v sub 0, or the absolute value of that, we're only calculating one distance multiplier, and that is this equation. And in this case, the vertical travel distance, d, is the vertical travel distance from the origin of the lift to the destination. And again, keep in mind that can also be negative. So you're taking the absolute value. A lift can definitely start higher and end lower as well. So d is an absolute value that you should be using in this equation. The next equation or multiplier here is the asymmetric multiplier. And this is a function of the asymmetric multiplier is a function of a. And again, the a is the amount of twisting that happens with the torso from the origin of the lift to the destination of the lift. So if a person picks up a load and then just raises or lowers it without twisting, that's an angle of 0. But if they do any type of turning, if they turn, say, 45 degrees and put the load over here, that's an angle of asymmetry of, say, 45 degrees. And that would serve to lower the asymmetric multiplier from 1 to some fraction. The next one is the frequency multiplier. So there is no equation for this one, but you do have this table. Now, and this table is a lot. So let me walk you through this table. There's a lot going on here. So to use this table, you first want to start with the frequency in lifts per minute. And you can see that the table goes from 0.2 lifts per minute, which is basically 1 lift every 5 minutes, all the way up to 15 lifts per minute, which, if you can imagine that, that's a pretty good clip. That's a lot of lifting going on. That's 1 lift every few seconds. And so anything greater than 15 pretty much automatically zeroes out this multiplier, which says, hey, this is an unsafe lift. But for lower lifting frequency, you can use this table. So you can see there are 6 columns, and they're subdivided into 3 lifting durations. Less on the far right, lifts for where you're lifting for less than 1 hour per 8-hour shift. In the center, we've got 1 hour, but greater than 1 hour, but less than 2 hours. And on the left, we have greater than 2 hours, but less than 8 hours. And so if the person, say, lifting for 2 hours out of the day, you would select from the 2 centermost columns. So if we're in those 2 columns, which of the columns do we use? Well, the answer is that depends upon the vertical travel distance, or the V, the distance from the floor to where the lift either starts or its destination. So V determines which of these 2 columns you select from. So if V is, say, 20 inches, you would select from this column right here. If it's greater than 30 inches, you would select from this one. And so so you just cross-reference. If it's 5 lifts per minute and we're lifting for 2 hours and V is 20 inches, well, you're going to use 0.6. If we're doing 2 lifts per minute and they're only lifting for 30 minutes a day and V is greater than 90 inches, well, you're using 0.91 as your frequency multiplier. So then finally, the last multiplier is our coupling multiplier, and that is also dependent upon V. And with that multiplier, we look at whether we have a good coupling, a fair coupling, or a poor coupling. And the good coupling is basically anything with handles and cutouts, where you can get a firm hand grip. The surface is dry and not slippery, and there's no sharp edges, and it's small enough to be held close to the body. A fair coupling would be something with partial or limited handholds, or it might have an irregular shape but still be handleable, or may require more grip force. A poor coupling would be no handles at all, awkward grip, sharp edges requiring it to be held gingerly or with special care, or it needs to be held with a lot of force. That would be a poor coupling. So these are how you calculate the various multipliers for the NIOSH lifting equation. So now what we're going to do is work through an example. I encourage you to download the spreadsheet that I've provided a link to in the description below so that you can follow along. And we're going to work through a scenario that I have prepared for this purpose. All right, so let's go ahead and dive into this example that we've prepared for this tutorial. So our scenario starts with a farmer unloading hay bales from a baling machine that land on the pallet, and then these bales are then picked up and loaded into the back of a truck in the field. So the specifics of this lift are as follows. A farm operator unloads 20-pound hay bales from a baling machine pallet to the back of a truck. The pallet is 10 inches off the ground. Each bale has wire grips located 5 inches from the base. The operator lifts each bale from a starting position with feet 12 inches from the lift origin, raises it 36 inches to the bed of the truck, and releases it 18 inches away from the body with a 90-degree twist. This task is performed every 20 seconds, 6 hours per day. So now we have all the information that we need in order to get the measurements for the NIOSH lifting equation. So let's do that. Okay, so we're going to start with these particular variables. Where we want h sub H, V, and A. So the horizontal distance, the vertical distance, and the angle of asymmetry, both at the origin of the lift and the destination. So starting with H sub O is 12 inches. That's from the center of the feet to the center of the load. And then H sub D, at the end of the lift, the problem statement said that the load was 18 inches from the body, so 18 inches from the center of the feet, rather. And so H sub D is 18 inches. Moving on to V, V sub 0, V sub at the origin of the lift is 15 inches. So why did I choose this? Well, because it's very important to remember that V is from the floor or the ground, not the surface where the lift starts. So one common mistake is that people would put V of 5 inches because the hay bale is resting on the pallet, but that's not correct. You have to take into account both the height of the pallet and the height from the bottom of the hay bale to the center of it. And so that total is 15 inches. So V sub O is 15 inches. Then our problem says that the load is lifted 36 inches to the back of the truck. So that is our vertical travel distance. And from that, we can derive what our V sub D is, or the vertical distance at the destination from the ground, which is 51 inches. Our angle of asymmetry at the beginning of the lift, the farmer is facing the pallet. So our angle of asymmetry at the origin is 0 degrees. However, the hay bale is picked up and subsequently rotated 90 degrees to the back of the truck and released. So with that twist of 90 degrees, A sub D is 90 degrees. Our angle of asymmetry at the destination is 90 degrees. So that's most of the information that we need to calculate the NIOSH lifting equation, but there's a few more things that we need, and let's get into that. And the important information that we need for these remaining variables is the following: the load weight of 20 pounds, and the fact that this task is performed every 20 seconds, 6 hours per day. That's our lifting frequency and our lifting duration. And also that the bales have wire grips that get into our coupling. So here's the data that we have so far. We've established that the weight load is 20 pounds. Our load constant is 51 pounds at both the origin and destination. That's going to be the same regardless of the task. That's the same for every application of the NIOSH lifting equation. Our horizontal location is 12 inches at the origin and 18 at the destination. Vertical is V is 15 inches at the origin and 51 inches at the destination. Our vertical travel distance is 36 inches, and our angles of asymmetry are 0 at the origin and 90 at the destination. So we still have a few more. We need lifting duration, lifting frequency, and the coupling factor. So our lifting duration is 6 hours per day. So that's just a straightforward, we plug in 6. And our lifting frequency, if we're lifting every 20 seconds, that boils down to 3 lifts per minute. And because the bales have wire grips, that means that the farmer lifting it can get a good grip on the hay bale. So we're going to say that our coupling factor is good in both cases. Now, as a reminder, here are the equations for the NIOSH lifting equation. And what we're going to do now is we're going to actually open up the spreadsheet and we're going to plug in the data that we just derived from our problem statement. So I encourage you to follow along in the spreadsheet. So here we have our spreadsheet, and let me go ahead and just quickly walk you through this. This is freely available in the link in the comments, or in the description below. And this spreadsheet has 3 tabs. This first tab is the actual worksheet, and there are cells that are editable. You can put in some evaluation information about the analysis that you're doing, the date it was completed, the task, who did it, what department it is, and what the names of the operators who actually performed the task. And then here is where we plug in the measurements that we've taken. The green cells are the only ones that are editable. All the other ones, the yellow ones, are actually calculated for you. So there's actually only a fraction of the data that needs to be put in. The spreadsheet will then automatically calculate both the recommended weight limit and the lifting index of the job, and will then color code it according to this breakdown that we discussed earlier. On the second tab, just for reference, here are some lookup tables that you can use to confirm that the calculations are correct in your spreadsheet. And also the equations themselves are here for your reference. And then the third tab is just a license use and agreement tab. All right, so let's get into this particular example. So I'm going to, just for reference, we have a picture of the various measurements for your reference. And we're going to look now at the data that we collected earlier. So let's bring that up, and we'll just start plugging in information. So let's put in a reasonable date. So I'm going to say this is July 2025, and this is the System Scholar video, and the task is the hay bale lifting analysis. And this Doc Romo is the evaluator, and the operators are Farmer Jim. Okay, all right. So now that we have our header filled out, let's start plugging in our data. Our load weight is 20 pounds, and since that's going to be the same throughout, you just have to type it in once, and it's automatically reflected here. The load constant will be the same always, so it always starts at 51 pounds. And now we need to plug in the H sub O and H sub D. So our H sub O, it was 12 inches, and our H at the destination was 18 inches. And as you can see, it automatically calculates the multiplier for you. And if you want to look that up and confirm, you can come over here and look at the H for the horizontal multiplier for 12 inches, and there it is, 0.83. So it pulled the right one from the table, or calculated. It's actually a calculated value. Now we need our vertical distance, and so from our data, we know that our vertical distance at the beginning of the lift, the origin, was 15 inches, and at the destination, it was 51 inches. And our vertical travel distance is just the difference between V sub D and V sub O. So that's calculated for you automatically. Our angle of asymmetry at the origin was 0 degrees. And at the destination, it was 90 degrees. So we're going to plug that in. Our lifting duration is 6 hours. That's actually a lookup. And so if you want to know whether to put in short, moderate, or long, just click right here, and it'll tell you that short is less than 1 hour, moderate is 1 to 2 hours, and long is 2 to 8 hours. So at 6 hours out of an 8-hour shift, that's definitely a long duration. So we're going to pull this down and report long. And then our lifting frequency in lifts per minute was 3 lifts per minute. And our coupling factor, we decided, was good. Now, if you need some clarification, you can just pull up the information. And here are the criteria for the coupling to kind of help you decide. We decided that it was a good coupling at both the origin and the destination of the lift. So let's look at the results. All right, so our recommended weight limit at the origin was 18 pounds, and at the destination was 81 or 8.1 pounds. And our lifting index at the origin was 1.11, and at the destination was 2.46. So the spreadsheet is going to automatically take the larger of the two lifting indexes. So it's that twisting and moving the hay bale away from the body, 18 inches, that made the destination the more risky aspect of the lift. It's not necessarily the beginning of the lift, but the end of the lift where you have to kind of lean and release the hay bale after twisting. So the spreadsheet will automatically determine which of these is higher and put it here, and it'll change the color appropriately. So looking at this lifting index, we can see that it falls between 2 and 3, which qualifies this particular lift as a high-risk lift. So this one would definitely be earmarked for redesign or elimination from this task. So this is a lift that definitely needs to be addressed. So there you have it. That's how to use the NIOSH Lifting Equation. I'm Dr. Matthew Romoser, and I've been doing this for about 25 years. And if you found this tool useful, please consider giving a like and subscribe, and feel free to download the spreadsheet and use it on your own list. If you do, I would love to hear from you and discuss with you what your results were. My contact information is right there on LinkedIn. So until next time, take care, and I hope to see you again.